Hello, can you hear me?
Yes, sir, we can.
Okay, and you can see the desktop now?
Yes, sir.
Okay, good. Let me see. Let me pull up some windows. Get the chat window up. Okay, so hello, this is the Programming Languages Interpreters and Compiler course. We're going to meet this way using Zoom for probably the entire semester. Okay. Um, I put a link to the Zoom meetings up on Brightspace, and most everything for the course is going to be on this course website. So on the Brightspace for the Brightspace site for the course, I also put a link to this course website. Well, beginning, I'll show you the course website. This is where you're going to find everything you need for the course. Okay, so everything is really here rather than on Brightspace. Okay, so for example, one way to get to the course is if you just Google my name. It'll almost always be the top link if you just Google my name. So this is the home page. These are the courses I'm teaching. So this is this course. Here's a link to the Zoom meetings for each day. This link should work for every meeting we have for the whole semester. And then office hours are going to be on Tuesdays and Thursdays using Zoom also. So here's a link to the office hour on every Tuesday, Thursday from 2:30 to 4. Okay, and then the website has essentially 4 pages. Well, this page is this one here. Then, for example, here's the syllabus for the course. This describes what we're going to cover in the course. There's no real textbook for the course. There's this online textbook on interpreters that's very nice. We'll use it partly, but most of the time, for most of the semester, I'll give you separate readings. I'll link to different readings on the internet that contain the material that we need to cover. And occasionally we'll also look into this book. This book is very nice. Right now we're going to do some introductory material on trees that isn't in this book. So we're going to be doing the tree data structure for a little while. And then we'll start talking about the actual interpreter code that's in this book. Okay, so this class is going to be programming assignments. There's not going to be any exam this semester. So the whole course will be based on programming assignments. There's going to be one every 2 weeks. So there's going to end up being about 8 programming assignments, one every 2 weeks for the whole semester. Okay, and the homework assignments, you'll be downloading them. See, here's the page that has the homework assignments. There's already the first one up there. We'll go over it in a minute. Okay, so this website has the syllabus and the homework assignments up there both. There's instructions here on how to turn in your homework assignment. We'll look at those in a little while. Okay, so the homework assignments are done individually. In this course, each person is supposed to do their own programming assignment write their own code for each programming assignment. The language will be Java, and you have to use Java for the programming assignments because I give you your code has to interface with my code. So the way the programming assignments work is I give you starter code and library code that I've written that you have to augment and add to and modify. So you have to, since everything I give you will be in Java, you'll be also writing your code in Java too, okay? And the version of Java isn't that important. Anything better than Java 8 will be fine, okay? Now, the other page on the website is this real important page here. This is the page that this lectures and reading. This is the page that describes what we do each day. There'll be an entry here for every day that we meet. And it'll give you, it'll announce when there's a homework assignment. It'll announce reading assignments. This is where I'll distribute example code that we're going to look at. Today we're going to look at this code here, something called language0.zip. Okay, so this page there'll be an entry in this page for every time we meet and the first link here is to the Zoom meeting itself. When class is over with, I'll replace this link with a link to the video of what we're doing today. So the meeting is being recorded and I'll put it up on YouTube, and then this link will be replaced by a link to the video itself. Okay, So every day there'll be a link to the course meeting, and then after the course meeting, there'll be a link to the video of the meeting, and there'll be like, homework assignments, reading assignments, and source code that we look at during class. The example code that we look at during class. So this is the page you need to look at real often to keep up with what we're actually covering. Okay. And then this page will have your homework assignments up there. There's already one homework assignment. We'll look at it in a minute. If you click, this is the description of the homework assignment. And the homework assignment comes with code, and that's in the zip file. Okay, you download. See, there's a zip file, and the homework assignment includes a fair amount of starter code, and that's in this assignment here. Okay, and we'll go over the details in a few minutes. Okay. So the website where everything is going to be for the course is the syllabus, the daily lectures, and the homework assignments. So the most important page is this one here, the lectures and reading page. That's the page that we'll go to the most often, because that's the page that describes what we do from day to day. Okay. Before digging into this stuff, anybody have any questions about the course in general? Oh, I can't see you. When we meet, well, I'll always just show you the desktop of my computer, because we're going to spend a lot of time going over code. So I'll be running, compiling, writing code in class, and we'll be talking about the code that I work on in class. So you won't see my face, and I won't see your faces. But that means if you have a question, just say it. If you have a question, just interrupt me. The easiest way to get my attention is just to interrupt me. If you could write something in the chat window, but the chat window's off to the side on a separate monitor, and I don't really see it all that often. Like I don't look over at the chat window very often during the class. Too hard to talk and be reading a chat window at the same time. So if you have questions while we're talking, just interrupt me at any time. And if you have a question about a code example, if you have a question about what we're doing, or if you want something explained again, please feel free to interrupt at any time. Now, does anybody have any question about what we've talked about so far, about the structure of the website, or about the way the course is going to work? Any question at all? Okay. Like I say, if you have questions during the class, please interrupt. That's the fastest way to get my attention, is just to unmute yourself and just bring up a point. Okay. All right. Now, this class is on interpreters and compilers, and the core data structure that we need throughout the entire semester is the tree data structure. So the first readings of the semester are 3 different explanations of the tree data structure, and they're taken from different data structures textbooks. So for example, this is a real nice older book on data structures here. This is a very nice explanation of the tree, what he calls the data model, the tree data model. Okay, so in particular, what we're going to be talking about starts on page 6 of this document, is expression trees. That's going to, in a minute I'll try to show you in detail. But expression tree is the key idea, the thing that ties interpreters and compilers to tree data structures. This idea of an expression tree. Okay, so if you read like the first 10 pages or so of this document, the expression tree continues from page 6 up through here, page 8. So you read the first 8 pages, you'll get a good little idea of what it is we need to start with. Okay, then similarly, here's another a data structures textbook. Now this links to the entire book. See, it's 600 pages long. The stuff about trees is in chapters 5 and 6. And the stuff on expression trees is actually, it doesn't say it in the table of contents, it's this section 5.3.1. You want to read that, you probably want to read chapter 5 up to the end of section 5.3.1. So here is the stuff about expression trees. See, starts here on page, on section 5.3.1, and there's some pictures of expression trees. So that's the idea that links what we're going to be doing in this class, interpreters, to tree data structure. Okay, so read the first, in this reading, you'd want to read at least, go back to the table of contents, at least up to the end of section 5.3. Okay, so that's like the first 10 or 15 pages of this thing here. And then as we go along and you need more information about trees, there's this whole, well, actually, the reading assignment is only sections 5.1, 2, and 3. We're not going to need search trees or heaps and Hoffman coding. We don't need this advanced stuff on binary trees. And for the section on non-binary trees, again, we only really need sections 1.2, 6.2, 6.1, 6.2, and 6.3. We're not going to be using any of these more advanced topics on trees. So that's like the first 20 pages of this chapter. Okay. And the emphasis again is on expression trees. And then there's another reading from another data structures book on, in this case, on binary trees. And if you scroll down here, there's where he talks about expression trees. Okay, and he gives an example here. So the key idea is for us is expression trees, and we're going to build on this idea of expression trees a lot. I mean, it's really, we're going to end up calling them, the more general notion of an expression tree is something called an abstract syntax tree. So expression trees are going to become abstract syntax trees, and that's what we're going to be working with a lot throughout the course. Okay, so the first reading assignment are the stuff about trees and expression trees in these sections here. Okay. Now let me show you the program, the homework. Before going over the homework assignment, let me download. There's a folder here of sample code. It's called Language 0. What we're going to do this semester is we're going to build up programming languages. We're going to go through a sequence of progressively more sophisticated programming languages. And I'm going to call the languages by a really creative sequence of names: language 0, language 1, language 2, language 3, language 4, language 5. We're going to go up through about 10 languages. And when we get towards the end, our languages will be essentially like a baby version of C and a baby version of JavaScript. We'll get up to a level of sophistication that's a simplified version of C and a simplified version of JavaScript. Okay, so that's when we get to languages 8, 9, and 10. Yeah. All right. So we're going to build interpreters for a sequence of languages, and that's what the book that I showed you was like nominally the textbook for the class. That's also what that textbook does. Where is it? Where is it? Okay. This book here also does the same thing. It builds a sequence of languages that starts off simple and makes it more complicated. And so, a lot of what we're going to be talking about is going to be in this book. And occasionally I'll give you readings from this book. If you want, you can start reading it. The first half of the book is interpreters. The second half of the book is on compilers. I'm not even sure we'll have time to get to very much of the second half of the book. The main goal is to do the interpreters real well, and maybe at the end of the semester, start with a little bit of an introduction to the compiler aspect of it. Okay, all right. So we're going to start with this language 0. Let me download it. Language 0 is a language of trees. Okay, so let me download the zip file and then unzip it. And your homework, your first programming assignment is based on this language 0. Okay, so here's all the code for language 0. So I don't need the zip files after I'm done. Okay. So here's a bunch of files that together create a really simple, essentially, it's not even a programming language. That's why I call it language 0. It's really a language of trees. Okay. And I'll show you in a second what I mean by a language of trees. Okay. And if you see, this is a little, I'm going to use a real simple build system. The build system is just a batch file that just compiles everything that's in the folder. Okay, so there's the call to the compiler, and it compiles all the files in this folder. So if you double click on that file, it compiles everything in this folder. So everything got compiled. Okay, and then if you want to clean up, you double click the clean full batch file, and it deletes all the class files. It cleans things up. When you if you make changes in the code and you need to recompile, it's a good idea to clean before you compile. Okay, so this here will compile one program. Like if you want to like this example here called language 0 example. If I drag and drop that on here, that compiles and runs this one. Well, in a minute we'll look at the code. See, it compiled and ran that program. Okay, and then I can click clean, and it'll delete everything that was compiled, that was created. I'm using now you need a version of Java on your computer. The version of Java that I got on my machine, and the one I suggest these days that people get, is Amazon Corretto. The Amazon Corretto version of Java, okay, this is the website for it. The best one to get is this Corretto 11. Oh, this is new. This just appeared in the last couple of days. They've now got a version for Java 15. Okay, I'm currently using Amazon Corretto 11. So if you click on this, you can download Corretto for whichever version of whatever operating system you're using. Like, so here is the Windows. I usually just download, download this is the Windows installer. This is a zip file if you don't want to install it, if you just want to download and unzip it, but there's the installer. There's the version for the Mac OS, and there's versions for Linux. Okay, all right. So that's the version of Java that I recommend these days, is the Amazon Corretto version. Okay, and if you want, you can even download the most recent one, the Corretto 15. I have not downloaded Java 15 yet. I haven't started. The reason they have the odd numbers here is 8, 11, 15. These are what are called the long-term support versions of Java. So Java 9 and 10 are no longer supported. So the ones in between here are no longer supported. 8 is still supported. Then 9 and 10 were just like temporary versions of Java. So they're not what are called long-term support. Then 11 was a long-term support version of Java. Then 12, 13, and 14 were not long-term supports. 15 is the most recent long-term support. So it'll stay up here now for a few years. And I think 8 will disappear in a little while. I'm not sure how, I don't know when its support actually ends. So Java's developed this idea of what are called short-term and long-term versions of Java. And pretty much the version of Java most people are using right now is 11, because 11 was the most recent long-term version, long-term support. So, and 15 just came out. It wasn't even there a few days ago. I think Corretto only put it up real recently. Okay. So on my computer, I have Corretto 11. Java 11 from Amazon. You can actually use any version of Java you want. You need at least Java 8 for what we're doing in this course. You need at least Java 8. If you probably should stick with Java 11, because if you use Java 15 and you use some feature in it that I don't have, I won't be able to compile your programs. So I would recommend that you stick with Java 11. That's the version that most people are. That's pretty much the most commonly used version of Java out there right now. And so that's the one I have on my machine. So that's what I can compile for. I can compile your Java 11 programs. Okay. So if you have Java 11, if you have this Amazon Corretto, if you download the installer, install it, then, for example, these script files will work. Then you can just, like, if you want to compile these programs, you can just, if you want to run one of these programs, you can just drag and drop, and the program runs. Okay, see, right? Same with the homework assignments. Okay, So I'm not using any fancy build system, just simple little script files. And these script files are so simple that if you have a Linux machine, all you have to do is change this just from CMD to SH, and this will work in Linux pretty much too. Okay, so these are pretty simple. You could use these things in as Linux script files also. Okay, and now here's how we're going to work. Here's what I mean by a language. See, there's this file here that says language0.txt. This file is the description of the language. Okay, this is called the language of trees. This is something called a grammar. This is a very short grammar. Now, grammars are also described in some readings on the course website. So if you go back to the course website, here's some readings on what we mean by what a grammar is. So you'd want to read, should be enough to read like these first, well, actually, if you want a good brief introduction to what grammars are, read this one, The Language of Languages. Okay, this is a website that does a very nice job of explaining what a grammar is. Okay, and another example would be this one here. What we're doing is, it's in general called context-free grammars. We're going to spend a lot of time talking about grammars as we go along. So right today we're going to do a real simple example of a grammar, and then we're going to build up to be more and more complex grammars. Okay, so read these two descriptions of grammars, and there's a like this one's also kind of nice to read. It's a PowerPoint from another course. And it does a nice job of outlining the idea of what a grammar is. Notice trees. Grammars, trees are very closely related to each other. Okay, grammars give you trees. Grammars, what we'll see is a grammar is a way of describing trees. Okay, so in this language zero is a language of trees. A tree, you read this, a tree is one of two things. It's this, or the vertical bar here is red as or. A tree is this or this. Now what you read this is, this means, the quotes here means you type, we're describing a language. So this is telling you what the correct strings in this language are. So a string in this language would be, for example, open parentheses. So a tree is an open parentheses, a string, okay? And then after the string would be, now this is recursive. A tree is a string followed by, the plus here is read one or more trees. So over here now, I've got left parentheses, string, and now I do another tree. So here's a tree. Now a tree is a left parentheses, a string, and then another tree. Okay, okay, so I'm going to do now or, but see, now here I can do the or part, or it's just a string. So here I could put dog. Okay, okay. Now notice that this is left parentheses, string, then dog is a one tree. Then I could close this parentheses here. This is a tree here, and that's this, that's that one of those trees. Okay, and then here's another tree. Okay, and then I'll close this. So here's a tree. The way we read it, this is the root of the tree. This is the left branch of the root. This is the right branch of the root. This left branch of the root has this as its root, and then it has this as its only branch. The right branch of this tree has apple as its root, and then it's got, that is, this apple has pear on its left branch and orange on its right branch. Okay, now here's how I would draw a picture of that. here's the root of the tree. It's got a left branch and a right branch. The left branch is cat, and cat's got only one branch, which is dog. On the other hand, the right branch of hello started off with a root of apple. Okay, then apple had a left branch and a right branch. The left branch of apple is pear, and the right branch of apple is, okay, notice it. See, I've here's what a tree is in the language. See, this is the language of trees. It lets me write a sentence that describes the tree. This is what we mean by the tree if we think of it as a data structure. The tree has this, the tree is an idea of there's a root and branches, okay? And this root has two branches. This one has only one branch. This one has two branches, okay? So there's an example of a tree. Okay. Now, here's another example of a tree. Here's another string in the language of trees. Well, there's a tree. A tree is a string. So there's a tree by itself. Okay. Here's another example of a tree. Okay. Now, what is this? If we look at the grammar, we have an opening brace, opening parentheses, that's this guy. String is that root. Then there is one or more subtrees. B is just a string, that's the first subtree. C is just a string, that's the second subtree. D is just a, so these are all one node subtrees. If I drew a picture of this one, it'd be a little bit, let's see if I can draw a picture. It would be A with a bunch of subtrees. So there's a branch, another branch. Let's see how many. So it'd be kind of like this. A's got a branch, B, C, D, E, and F. Okay, so there's an example of a tree. Okay, A, if we can make it look a little bit better. Make it look a little bit more tree-like. Okay, see, so there's a tree with root A and 5 branches, and each branch is just a root by itself. Okay, so the language of trees lets me describe trees by writing out things like this. So this is a string. Now, if I want, you can put quotes around these. This is a string in the language of trees. This is a string in the language of trees. So that's a what, you know, and here's a string in the language of trees. Okay. So this grammar describes this language of trees. It says that a tree is a literal, we call this a literal. When I put little quotes around something, that's called a literal. So a tree is a left parentheses, followed by any string, followed by, and this is the recursive part, one or more trees, and then a closing parentheses. When you do the one or more trees, you recursively use the tree structure. So like in this case here, that's a tree, and that's a tree. So there's the recursive part. And then if you look in this picture, you know, this is a tree here. That's a tree that forms the right branch of this tree. And this is a tree that forms the left branch of this tree. So trees are, that's why this, in the reading assignment, if you go back over here to the reading site, notice that the, 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 the book called its stuff on grammars recursive descriptions of patterns. See, recursive descriptions of patterns. That's what we're doing here. We have a language that lets us recursively describe patterns of what these strings look like. These strings that represent trees, they have a pattern to them, and this thing describes that pattern. This grammar describes that pattern. Okay, so a tree is made up of a root and subtrees. So a real quick way to say it is a tree is a root with subtrees and any number of subtrees. So one or more subtrees. Oh, now let me show you something that's not a tree. This is not a string. This is not a tree. Somebody tell me, what's wrong with that? Why is that not a tree?
Doesn't have anything after the string.
So if you look at the grammar, like you might, like it might say that, oh, this is like this one. You might say, well, it's a tree of just one node. A is the root, and that's all there is. But that's not the way the grammar works. The grammar says that it's either a node by itself or a left parentheses, a root, and one or more trees. See, this doesn't have any one or more trees after it. Okay. Another example would be something like this. That's not a tree. Even though you might think it's the same thing, you might think it was, oh, there's a root A with a branch B and a branch C. That's not what it's saying. That's the wrong way to say a root A with a branch B and a branch C. That's not a tree. Because a tree says that if you have the open parentheses, there has to be a string and one or more subtrees. Okay, so this is not a correct piece of grammar, and this is not a correct, these have syntax errors. So this has got a syntax error, and this has got a syntax error. The correct way to say a root by itself is like that. So this one's wrong. This would be correct. Okay, this one is wrong. What you probably meant was A with left branch B and right branch C. Okay. Okay. That would be this tree here of a root A with a left branch B and a right branch C. Okay. So the grammar says that a tree has either, see, this guy here is read as either. It's either a string by itself, which means it's just a root, or it's a left branch string, a bunch of trees, and then a closed parentheses. Now, the way you think of this is this stops the recursion. See, this is recursively saying a tree is made up of a left branch, string, and more trees. See, if I didn't have this here, this thing would be infinitely recursive because it would tell you that a tree is a string made up of trees. But then each tree is a string made up of trees. Then each tree is a string made up of trees. And there's nothing to stop the recursion. Okay, so it's a lot like writing a recursive function. Something has to stop the recursion. That's what this guy does. This guy, you can think of it as the thing that stops the recursion. The thing that stops the recursion is one of these trees is just a string by itself. Okay? So that stops you from just keep on going and going and going. So like in here, this, like here, this one, there's the root and there's the tree. That's one of these subtrees. That one subtree is, there's the left parentheses, there's the root. Now this guy is that. That stopped the recursion. So then that stopped the recursion with just one subtree, and then this closed the branch. Okay, then you go back up to here. Okay, right? So we've got a language now for describing trees. Okay, now let me show you what's interesting about that. If I write something like 3 plus 4 times 5, you're all pretty used to that. You've been dealing with things like that since grammar school, okay? So that's a way of saying do some arithmetic. Take the number 4, multiply it by 5, then add on 3. Okay. Here's a way to write that as a tree. That expression says you're going to take the sum of two things. You're going to take the sum of 3 with something else. Okay. Now, what are you adding? You're adding 3 to what? Well, you're adding 3 to the product of something. See, you're going to add 3 to that product of four and 5. Okay? This is what we call an expression tree. It shows you the structure of this thing here. Okay? Now let me do a slightly different version of this. Suppose I write 3 plus 4 times 5. Notice that that's not the same expression. This expression says, this one says, I'm taking the product of two things. I'm taking the product of something on the left with something on the right of the product symbol. The thing on the right of the product symbol is a 5. And the thing on the left of the product symbol is a sum of 3 and 4. What I've done is, remember, what I did here is I changed the order of operations. By grouping, I said do the 3 plus 4 first. See, here the order of operations is you do multiplication before you do addition. So this expression has this expression tree. And it's the same as if I put parentheses. It's the same thing as if I did this. That doesn't change anything. Okay. What's interesting is notice that in the expression tree, there's no parentheses, because the structure of the tree says you do the addition before you do the multiplication. Because see, you have to do 3 plus 4 before you could do the multiplication. So that says this is grouped first, followed by the multiplication. Where here, this says this is grouped first. You do the multiplication before you do the addition. Okay? But if this is a tree, we can write this in our tree language. So let's write this tree in our tree language. In our tree language, this tree would be what? It'd be, there's a left parentheses, because it's a tree that's not just a single root. The root of the tree is a plus. Then it's got a left branch, which is just a root by itself. Then plus has got a right branch, which is not a single root, single node, so it needs the parentheses. Then it's got a product of a single node 4 and a single node 5. That ends the subtree, and that ends the whole tree. Does anybody know what you call this guy here? Maybe you've seen this. This has got a name. You may have seen it. You should have seen it in your data structures class. What's that called?
Pre-order.
Pardon me?
Pre-order.
You're breaking up. What is it?
Can be pre-order. Pre-order.
Yeah,
tree.
prefix. It's called prefix notation. It's writing arithmetic in prefix notation because you're putting the operators before the operands. This is called infix notation. This is actually called prefix notation because the operators are before the operands. See, the operator is before the operands. So notice how our tree language is another way to write arithmetic expressions. This is going to be the thing that ties what we're doing. It's going to tie grammars with trees with interpreters. Okay, because here's what you want to do. You know, how would you write a program that if you type in either this expression, one of the classic problems in computer science is write a program that if you type in that gives you the answer, which is 23. How do you go from this to evaluating that to get the number 23? How do you go from this to evaluating it to get 35? See, the evaluation of that would give you 5 times 7, which is 35. Okay. What we're gonna do is we're gonna see that there's the way to write an evaluator for something like this is to build this expression tree and then do a post-order traversal of this expression tree. Okay, that's something we'll talk about later on. We're going to do a post-order traversal of this expression tree to evaluate this thing. So we'll write code that takes this, converts it to this, then does a post-order traversal of this to give us the answer. This string, so we'll think of this as a string, which is equivalent to this string in our tree language. Okay. Well, we're going to write programs that take this string, build this tree, and then evaluate the tree by a post-order traversal and tell us that the answer is 23. On the other hand, our program will take this string, it'll build this tree, which is the same thing as creating the expression tree. In this case, the expression tree is going to look like this. It's the root is a times, its left branch is a plus of 3 and 4, and the right branch of the times is a 5, and that closes the tree. Okay, so there's the tree in prefix notation. We're going to write code that takes this, creates this tree, and that's going to evaluate that tree. It'll go do 3 times 4 is 12, then 12 times 3 plus 4 is 3 plus 4 is 7, then 5 times 7 is 35. Over here we'll do 4 times 5 is 20, then plus 3 is 23. We're going to do post-order traversals of these trees to evaluate them. So we're going to have a tie-in between grammars, trees, and what's eventually going to be arithmetic expressions. Now let me show you another example of what we're going to do that's interesting. Here is something out of a piece of code. If x equal y, print x, else print y. Okay, there's a string of like Python-like code. Okay, I'm going to turn that into a tree. It's an if tree. The if tree is going to have 3 branches. It's got a conditional part, a then part, and an else part. The conditional part in this guy is a tree with a equal equal operator, and the equal equal operator has 2 operands, x operand and a y operand. Okay. Now, what about the if part? The if part is a print command, which has just one operand, which is x. And let's see, can I, oh. Try to space this out as a nice looking tree. And the else part is another print. It's another print, and it has as its subtree y. Whoops. This piece of code can be represented by this tree here. Try to make it look nicer. Okay. Okay. So there's a tree that represents that piece of code. Okay. Now, but if that's a tree, I can write its expression tree. But except here, I'm not going to call it an expression tree. I'm going to call it an abstract syntax tree. The abstract syntax tree, so this tree here is, instead of me calling it an expression tree, I'm going to call it an abstract syntax tree. What would our grammar say it is? It's a tree with root if. The if expression has a left branch, which is an equal operator with x and y. And then the if branch has a center branch, which is a print with one child x. And then it's got a right branch, which is a print of one child y. Okay. This looks like Python, for example. Does anybody recognize this language? This is actually a real programming language. Does anybody know the name of it? Have you ever seen it? Any of you know which language is written that way? Anybody? It's like the prefix notation here. This is the syntax of a whole slew of languages. It's Lisp, Closure, Scheme. Okay, those are the languages that are written this way. So, for example, if I go over here and I Google Lisp, okay, see if I get a Lisp example. And let's see. Boy, there ought to be an example here. Here, see? See? Left paren, root, left branch, right branch, root tree, root, right branch, close, close. See? See how the language is written? See here? The root with 1, 2, 3, 4 child branches. Okay. Another example of a language that's written this way is Closure. See if I get an example of Closure. See? See how it's written using tree. Notice how the language is written using a tree notation. These are languages written using this tree language. Okay. Another famous example is Scheme. There's the root of the tree. There's a left branch. Then here's a right sub-branch. Notice that you could have here, this one allows empty branches. There's a slight variation. This scheme has a slight hitch to it where you could have an empty tree, okay? But you can see that they're basically writing the language using trees. See, the language is written as trees. This is actually a programming language, okay? The tree language is the Lisp scheme. Another one is Racket. Oh, the name of the language is Racket. The Racket programming language. See, it's written in this tree structure. Left paren, that's the root of the tree. That's the left branch. There's another tree. Here's the root of the tree. There's a node, a node, a node, close, close. Okay. The programming language is a tree language. Okay. So these are famous. This is a famous family of programming language. They're all derived from Lisp. That was the first one. Lisp, Scheme, Closure, Racket. Okay, they're famous for one thing being that they're written in this tree language. Okay. So our goal is to turn these ideas into a way of writing interpreters. So what we're seeing right now the tie-in between trees, code, and our tree language. Okay, so this is, you might think of it as, this is code. Okay, this is the abstract syntax tree for that code. Okay, and then this is the tree language version of that code. And this stuff works, you know, and the languages that are like this are well, okay. So we have what looks to us like code. This could be BASIC or Python or even something like, or C, for example. If X is equal to Y, print X, else print Y, okay? Yeah, if it was actually C, you'd need a semicolon here, and you'd need a semicolon here, you know, to make it C. So if you leave it as Python, then you don't need the semicolons, okay? But you can see that this is very much looks like a programming. This looks like one line of code from a programming language. When you write an elaborate piece of C code, you're actually writing a big tree, what we call the abstract syntax tree. Every piece of code is an abstract syntax tree, okay? Oh, another word for this is in the case of, if you type HTML code, another example I might do is something like, here's the source code to my web page, okay? This is actually a tree. There's the root of the tree. The HTML tag is the root. This is the first child branch. It goes from there to there. It's got a bunch of sub branches. Then this body is another sub branch of HTML. So this is the root. It's got this as its left child. It's got the body as its right child. And this body is a much more elaborate tree. When you take this tree language and you draw the tree for it, the tree as a name is called the DOM, the Document Object Model. Okay, in the language of web browsers, it's called the Document Object Model. The Document Object Model is this abstract syntax tree for web pages. Okay, the HTML of a web page is a tree. You kind of can see it over here. You takes a little bit of work, but that's the root of the tree. You notice it's even formatted kind of tree-like. There's one branch. with that's a sub-branch, there's another sub-branch of this branch, until you get, this is the end. So this is the first subtree of this. And then the body, which actually goes all the way to the end. So this HTML, the root has two branches, the head and the body. And then under the body, there's a whole bunch of branches. Okay, that's forming a tree. That tree, when you write it all out and you draw it out, it's called the DOM, the document object model. So this is a real core idea of all computer programming languages, that a programming language that really describes a tree. And it's the tree structure that you work with. Okay, you work, compilers, interpreters, web browsers, all of them, what they do is they take your source code, and the first thing they do with it is translate it into some kind of tree structure. Then they process the tree structure. In programming languages, we call the tree an abstract syntax tree. Okay, in arithmetic, we call the tree an expression tree. In programming languages, we call the underlying tree the abstract syntax tree. In the case of web browsers and HTML, the underlying tree is called the document object model. Okay, the DOM. Okay, and the most general term is parse tree. It's what's called a parse tree, because there's always something to do with a grammar. This is always tied to some kind of grammar. So grammar, tree, and we're going to tie these together. Programming languages, grammars, and trees. Eventually, over the course of the semester, we're going to tie these things all together. Okay? All right. So, okay, let's see. Now, let me close these things. Now, language 0 is this tree language. Now, these are just, the language itself, the big difference between language 0 and these programming languages is this language doesn't give any meaning to these trees. They don't mean anything yet. For example, right now, this doesn't mean do arithmetic. As a tree here, it just says that's a tree. This just says that's a tree. This just says that's a tree. To turn it into a programming language, you have to give a meaning to these trees, what's called the semantics. Right now, we're just looking at the syntax. Then eventually we'll have to give meaning, which is the semantics of the trees. Okay? Now, what we want to do next is turn this into code. That's where this folder comes in. Okay. So what this folder does is for example, here is a file that describes a tree data structure that can hold these that can actually encode these trees here. So for example, now if I open that and look at the code to it, in Java, a class that's a tree, what is it? It's a root element and a possibly empty list of trees. See, a tree is a element and a list of trees. Now, notice that doesn't quite jive with our grammar. Okay, this is actually a problem in Java. Java's a little bit of Java's not the most modern programming language in the world. And one of the goals of modern programming languages is to do a better job of matching descriptions like this with your code. Okay, Java doesn't quite nail it. See, what is a tree? A tree is either a root and subtrees, or it's just a root. In Java, a tree is always a root and a list of subtrees. But this list could be empty. So what we do in Java is this case is actually this guy with an empty list here. And this case is this guy with a non-empty list here. Now that's not really great, okay? And more modern programming languages let you actually do this a little bit better. They actually, some of the modern languages like Rust and Haskell, they actually do a better job of saying a tree is two things. It's either a root with subbranches, or it's a tree by its, or it's a root by itself. Java kind of fudges it, okay? Java says that every tree has a root. Well, that's true. I mean, every tree's got this string. So that part, okay. But this part's a little bit, here, this says a list of subtrees, okay? Well, a list doesn't have to, see here, this was one or more. Remember, this was one or more. Remember, we said that this was a syntax error. You weren't allowed to have an empty, but that's exactly what Java does. Java essentially does this. Java essentially does this wrong thing. It basically says that A by itself is element A and an empty list of subtrees. Okay, and that actually causes bugs in code. The fact that Java doesn't do a 100% accurate reflection of this grammar causes subtle bugs when you're trying to write the code to this. If you're not careful, you can introduce subtle bugs in your code because Java doesn't give you a good way of saying this. There's not a good match between what Java says and what the grammar says. There's a lot of overlap here, but not quite 100%. Okay, so in Java, a tree is a class, it's an object holding a string and holding a list of more tree objects. And if this list is empty, then we treat it as that case there. Okay, now we have a constructor, okay, for trees. Okay, notice that the constructor is written in this style here. What this is saying is that the constructor takes an element here and zero, or now here, see this dot 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 is a way of saying something like this plus here. This is saying that there are 0 or more parameters here. Okay, this is what's called variable number of arguments. So when you call the tree constructor, you can give it one parameter, which would be this, or you can give it more than one parameter where the other parameters are going to be trees. Okay, we'll see in a minute what that looks like. So the tree constructor kind of looks like this, but it actually looks like this where this is 0 or more, where really this is supposed to be 1 or more. The constructor is this guy and 0 or more subtrees. Again, the Java doesn't quite match the grammar 100%. Okay. Okay. Now, notice that here I do an if statement where I check the length of this subtrees. See, subtrees is an array of trees. In Java, what this is an array of trees. The array might be empty. So I ask, is the length of that array non-zero? So if the length of that array is non-zero, then I have to create the subtrees. Okay. But if the length of that array is 0, then I'm in the case where the array list is an empty array list. Okay. Okay. So now, then I have a get element from the tree. I can add subtrees. Now that's not, this is where Java really diverges from what's over here. Over here, you're describing a tree. You're not manipulating the tree. So this says this is what a tree is. It doesn't provide a way to add branches to the tree, but Java does. Here we allow you to add subtrees to a tree. Okay, so you can add to a list of trees. You can add a subbranch to a tree. Okay, and you could get a subbranch from a tree. Okay, and if you read the references on trees, we have words like degree. Degree is when you count how many branches a node has. Like this branch here has degree 5. This branch has degree 2. This has degree 1. This has degree 2. Okay, so the degree of a tree is just the size of the list of subtrees. Okay, and the depth of a tree is how many layers there are from top to bottom. So this is a tree. Now, you got to be careful about depth. Is this a tree of depth 2 or 3? Because you can look at this tree and say that's 1, 2, 3 layers, or you can look at this tree and say that there's 1, 2 steps to the tree. And different people actually have different ways of describing depth. Some people, in some books, this is a tree of depth 2. In some books, this is a tree of depth 3. In some books, this is a tree of depth 1. In some books, this is a tree of depth 2. Okay, so and some this would be a tree of depth 0 or a tree of depth 1. Okay, what is it over here? Okay, notice that it's the depth function starts off by saying that the result, the depth is going to be 0. Then if the degree, if there are branches, then it goes down and counts how many branches there are. If there are no branches, so if it's a tree that looks like this, if there are no branches, then it returns 0. So this definition of depth, this is a tree of depth 0. So this would be 0, 1. So this is a tree of depth 3. And this is a tree of depth 2 in our way of doing it. That's why we're going to do it in this class. So we're going to count how many layers are in the tree, not how many branches there are from top to bottom. Different people do it different way. This thing's got 1, 2 branches from top to bottom, but it's also got 1, 2, 3 layers. So for us, depth will be the number of layers. That way, the smallest tree is depth 0. Okay? Instead of having depth 1 for the smallest tree has depth 0. Okay? So there's the function that computes the depth of a tree. And then here's a function that converts a tree to a string. What this does is it goes backwards from this picture to this string here. This toString function will take this data structure and stringify it as, I lost my mouse. Okay, it'll take this structure and stringify it as that kind of a string there. So it actually goes backwards. It goes from the tree data structure to the tree language. That's what the toString method will do. Okay, so we've got a Java file that lets us build trees. Okay, now here's a file. Here's an example of how we would use it. Suppose I want to build that tree. Now here the tree is written as, it's drawn as a picture. I didn't write the tree grammar for it. Here I drew the picture of it. A tree with a root A, 3 subbranches. The left branch has 2 subbranches. The middle branch is just by itself. The right branch is, okay. Here's what that tree looks like in Java as a bunch of constructor calls. The tree is a new tree with root A. Then that tree has, remember the tree constructor says you construct a tree from a root and a possibly empty sequence of more trees. Okay, so here's the root, and here's 1, 2, 3 subtrees. So I'm calling this constructor with a root, and then here's a subtree, here's a subtree, and here's a third subtree. Okay, now this tree has got a root and 2 subtrees. Okay, now notice that when I want to create a tree with 1 branch, see, when I want to get down to here, which is the case in our grammar of just string, I do that with a constructor call that just has the root in it. So there's the tree creating a tree with a root and no subbranches. Notice I used the same constructor. I'm still using this constructor, but now I've got 0 ones of these parameters. See, this ... means 0 or more. You know, the plus here meant 1 or more. Technically, that's what we really want. This thing is 0 or more. That's Java's way of saying 0 or more tree structures. So that's used here. Here's calling the tree constructor with a root. Here I'm calling the tree constructor with a root and 3 subtrees. Here I'm calling the tree constructor with a root and 2 subtrees. Here I'm calling the tree constructor with just a root. And then here's another root. That ends the, that builds a tree there. Okay. And this builds a tree here. And then this one, okay, builds this, this part over here. Notice that this stuff can get hard to read. Notice that this can be, oh, and then see this line up here? This is that whole line written as one long line of Java code. To show you how unreadable Java can be, there's that, I constructed the tree 3 times. Here's an unreadable way, here's a much more readable way, and here's even a slightly more readable way. Tree A, it's got 3 sub-branches. This branch has got B with 2 sub-branches. This is just C, and this is D with 1 branch that's got 3 sub-branches. So D has got 1 branch, and its 1 branch has 3 sub-branches. So it's a slightly more compact way of writing this one. This is the real unreadable, yeah?
The bottom one looks like the tree output on Linux.
Exactly, that's where it came from. Yeah, and your homework assignment is essentially to write code that reproduces these. Yeah, see, there's, the idea is this is a fairly compact way to write the tree. This is a little too verbose. This is way too unreadable. That's unreadable, too verbose. This is kind of a nice way to describe the tree, okay? It's called pretty printing. We call this pretty printing the tree, okay? All right, so this builds that tree, okay? And then you can do things like you can process the tree. Now, let me compile this code and run it. Notice that it printed out the tree in a different, it printed out the tree in another way. This is another way to print the tree. See here you have root A with branch B, branch C, and branch D. And we see this is similar to the way Linux would print out a directory, like when you do a dir command and you ask for the directory structure of a bunch of directories. This is similar. Directories are trees. So this would be like saying this is the root directory. It's got subdirectory B with 2 files in it, and A has a subdirectory, and A has 1 file. A has a subdirectory B with 2 files in it. A has a file C in it, and A has a subdirectory D with a subdirectory G with a subdirectory H with 1 file in it called K. That's how Linux would show you subdirectories. Okay, so this is another way to print out the tree. This is a lot like the way we built the tree. A, B, E, F. A, B, E, F. See how those 4 lines line up with those 4 lines. There's C by itself. There's D, G, H, K, D, G, H, K, I, J. Okay, so see how this pattern here matched that pattern here. Your homework assignment is to write the code that prints this tree out like this one, to make the tree look more like that. Your homework assignment is to write what we call a pretty printer that'll take this tree data structure and print it in the way that looks more like the way this constructor call was, so that E is in line with the A, B, and E are all in line with each other. So the A, B, and E are all in line with each other with the F down below them. Oh, this got indented wrong. Okay. And then the C is 1 line. And then notice how the D, G, H, and K are all in line with each other. And then the I and J are lined up with the H below them. Okay, that's another way to pretty print this tree. And that's what your homework assignment is actually to write the thing that prints out the tree. This pretty printer here is done by this program here, the pretty printer. Your homework assignment is to write a better pretty printer. This pretty printer created this output here. It read the tree data structure. See, it took in the tree data structure. It took in a tree data structure and it printed out the tree data structure this way. And your code, your homework assignment is to print this tree data structure in the way that looks more like this constructor call. Okay? All right, so on Wednesday, we'll keep digging through this code. Okay, so we've covered the idea that we need. Yeah, we've covered the idea here pretty well. The tree language. So the tree language is described in those readings on the course homepage. Now we're going to start digging through the code that processes these trees. We want code that builds trees and code that processes trees. Okay. All right. So we'll quit there. Oh, one last thing. Notice that when I ran that program, it actually generated pictures of the tree. We'll talk about that on Wednesday too. I'm using a program called GraphViz. Okay, and if you look in this program, here's where you can download GraphViz from. So if you take that URL and put it into a browser, it'll download the GraphViz program, and you unzip it and put it on your C drive, and then this program will run GraphViz. There's the command to run GraphViz. GraphViz will draw these pretty pictures of the trees for us. So we'll talk more about that. This is you don't have to write the code to do this. The code is already written in these demos for you, but you have to install GraphViz on your computer, and then you'll get these nice two-dimensional pictures of the trees instead of something that mimics this kind of thing here. See, this picture mimics this picture here. Okay, whereas this is not a two-dimensional picture. This is just ASCII code. So this is the best we can do for drawing trees in ASCII. And well, I mean, this is the best you can do in ASCII, but this is real hard to write code for. It's hard to write code that draws these kinds of trees. It's not hard to write code that draws this kind of a tree. This kind of a tree is pretty manageable in code. Doesn't take very much code to write this. That's a lot harder. And this is way harder. That's what GraphViz does. GraphViz draws you these really nice pictures. Okay? But it does it from the tree data structure. It takes the tree data structure and gives us this output. Okay, so we'll play around with more of this on Wednesday. We'll keep digging through the code, and you can start reading the homework assignment now too. I think we've described enough to describe the homework assignment. Like, your homework assignment essentially is to write a better pretty printer. To write a better pretty printer that does output like this, but looks better, more compact output than this does. Okay, so read if you go to the homework assignment page, the description of what you need. This describes what you need. See, there's the pictures of the tree, and there's a description of. See, here's the description of the different kinds of pretty printing. Okay, you have to write code that does. See, here's the verbose pretty printing. That's the one I give you. You have to write this slightly more compact pretty printer and this slightly more compact pretty printer. You have to write two pretty printers that goes from, see, here's the single line, unpretty printed. Here's the verbose pretty printed that I give you. Then you have to write this one and this one. So you have to take the tree data structure and output it looking like this and this. Two different pretty printers. Okay, and I give you one pretty printer to look at. That's this one here in language 0, and you have to modify it to create these other two pretty printers. Okay, so we'll keep talking about the details of that on Wednesday. So read the introductory material about trees. and look, explore this code, the tree data structure, and this program that uses the tree data structure to build trees and print them out. Okay, so we've run out of time. So what I'll do, the class we just did is being recorded. So after class, I'll upload it to Brightspace. I'm sorry, I'll upload it to actually YouTube, and I'll put a link here to the lecture. So if you want to watch it again, or if you want to review any piece of it, this link here will turn into a link to the video. Okay. Anybody got any last minute question? Any last minute question about what we talked about?
My name is Aditya, and my query was, so we can use the program that you have written, and in the in the last part of the pretty printer, we need to remove that part, and we need to retype the better pretty printer, right?
Well, yeah. If you look at this, the homework is, if you download the homework folder, you're gonna write this pretty printer and this pretty printer. These are empty. See, they're empty. You have to fill them out. And I give you this. Here's a real basic pretty printer. And then here's another basic pretty printer. So I'm sorry, you have to write 3 pretty printers. I give you a real basic pretty printer, and then you have to write 3 pretty printers. A real simple one, a slightly better one, and a slightly better one. So you have to put code in here, here, and here that improve on this bare bones pretty printer. Okay. So, and that's what you're gonna, so your job is to write pretty printer 1, pretty printer 2, pretty printer 3, and homework1.java will actually test your code. See, this is written, and this will call your pretty printers, and it'll generate output, and the output should look like this. When you run when you're done and you run your program, you should get this output. Okay, that's all explained in the course website. But you're going to write pretty printer 1, pretty printer 2, pretty printer 3. You'll compile homework 1, run it, and the output is supposed to look like that. So that's your test case. And this is your test program. So actually, it's kind of misleading. Your homework is pretty printer 1, 2, and 3. The thing called homework 1 is really the test program. Okay, so it's written for you. It'll run your pretty printer 1, 2, and 3, and you should get that output. Okay? So your homework is to write pretty printer 1, 2, and 3. Okay, so I'll go ahead and stop here. Anybody else have another question? Any other question? I have office hours on Tuesday, Thursday at 2 o'clock, 2:30. So if you have questions, you can also stop. You can. It's Zoom office hours, but you can partake in the Zoom office hour. There's at the course website. There's a link to the office hour. So that's the Zoom meeting for the office hour, Tuesday, Thursday, 2:30 to 4. Okay. All right. Okay. So I'll quit now. So I'm going to just stop sharing, and then we'll meet again on Wednesday, and we'll go through. We'll keep on going through this language 0 code. Okay. Goodbye.